Hi, good afternoon. This is the second lecture in the series on Lagrange multiplier, and probably this will be the final lecture. So since we already given enough motivation, okay, in terms of implicit function theorem, geometry, tangent vectors, etc., today my goal would be to give a very precise version of the theorem and give a very neat, clean proof. And if time permits, we will also give my favorite application. Yeah, so let us get started. So what does the theorem say? The theorem says the following. This is the theorem, Lagrange multiplier. We already stated it perhaps, but it's worth writing. Okay, what does the theorem says? Let U be a non-empty open set. Let F from U to R be C1 continuously differentiable, and let G from U to RK. Okay, maybe I will write it as Rn plus K. Okay, yeah, let be C1. Let P equal to A comma B be an element of U. Assume that G of P is 0 and dg of P has rank K. Yeah, so let S be the level set of all x. If you want x comma y in U, which is a subset of Rn cross Rk, Rn plus K, so that G of xy is 0. Right? Assume that there exists UP open neighborhood of P in Rn plus K, so that okay, yeah, f of x is less than equal to f of P for all x in, okay, again if you want x comma y, so let me just write as xi for all xi in U, UP intersection. Yes, so look at the picture. This is my U, this is my UP, and this is my S, and this UP intersection S. Okay, right. Okay, then there exists scalars lambda 1 to lambda k, so that nabla f at P is lambda 1 nabla g1 at P plus dot lambda k nabla g at k at P, and these lambda 1 to lambda k are called Lagrange multipliers. So we want to give a proof of this theorem. Yeah, right. Now let's get started. Since I had given enough motivation, etc., let me stick to the proof directly. Okay, what does it say? Right, so what should I start with? Okay, so let us look at yeah, since we assume that nabla g at the dg at P has rank K, therefore by implicit function theorem, there is an open neighborhood U1 containing P in U, and an open neighborhood V containing A in Rn, and a C1 function G from V to Rk, such that U1 intersection S is nothing other than set of all xy in U, such that y equal to g of x and x in V. That is nothing other than this graph of since I already used this, let me call it H, a C1 function H, graph of H. Remember G I already used for constraints. Okay, this is the theorem, right? So now let's look at, okay, the map h of x defined again the way we did implicit function theorem, how we invoked inverse function theorem to do implicit function theorem. We are going to do the same thing. Let us define hv to r, okay, rn plus k. How do I define h of x? Can you guess? Yes, h of x. Remember this is an rn, right? H of x is x comma dx, right? Now notice that a belong to b and h of a is nothing other than b, so that p is ab. Okay, this is all part of the implicit function theorem, right? Now what is dh of x? Let me say even at a. So let us compute the Jacobian matrix. Okay, so this, let me write h of x in terms of components. It's x1 to xn and h1 of x to hk of x, right? Okay, so what is the Jacobian? If you remember, let us okay, Jacobian should be what kind of a matrix? My h is a map from something to with v in rn to rn plus k. Therefore the Jacobian matrix must be n plus k times n. And how does it look like? Say, look at this n plus k, therefore the matrix is, okay, del x1 by del x1, del x2 by del x1, del x1 by, let me write it, if this is the first time you are coming to me, and etc. del x1 by del x1. After that dg1 by dx1 and dgk by dx1. Okay, this is the nth thing, this is n plus k thing, right? You understand? So all these things are with respect to 1. Therefore what will be the kth nth one? That will be again clear. Okay, so that will be del x1 by del xn and del x2 by del xn and del xn by del xn and del g1 by del xn and del gk by del xk dot dot dot. So this is nothing other than, you can see this is 1 1 1, okay, right? And then after that del of g1 to gk by del x1 to del xn. So this is the identity matrix and this is n cross n. Yeah, I hope all of you understand. Right, very good. Now what is the rank of this matrix? Okay, at any x itself you know this rank. Notice that h is a map from some open set in Rn to Rn plus k. Okay, therefore the matrix of size n plus k cross n. Therefore the maximal possible rank is n, but we already have n rows which are linearly independent. Therefore rank of this must be equal to n. Is that clear? Pause, review, proceed. Okay, keep this in mind. Okay, right. Therefore DHK will be a linear map from Rn to Rn plus k. Therefore the image or the range of DHA is n dimension. Okay, keep that in mind. Now let us look at what I want to do is I want to look at f composite h. What is f composite h? Okay, now h, remember this is a function from b to r now, right? So I can as well assume by shrinking the domains etc. Okay, my h of b lies in u1. Okay, what is u1? u1 is the one which says that this happens, right? Okay, this kind of thing you should be clear, so we should not spend time on such things. Okay, so we are assuming hs. Okay, by continuity you can assume there exists instead of b some other b dash contained in b such that h of b dash is contained in u1. Therefore instead of b we will restrict to b dash. So are you comfortable? No, if you are going to get into analysis, this kind of things must be trivial. Okay, very good. So this happens, right? Now what do I know? Now remember what is h of a. So h of b is contained in u1, and I know on u1 intersection s the point a comma b, namely a comma h of a. This is a point of local maximum. Similarly, minimum for f on u1 intersection s. Right? Do you follow that? Therefore, it follows, therefore, for every x and b, what is f of h of x? And the relation between h of a, this is going to be f of x comma hx, and this is f comma ab, which is f of b, and x comma hx is going to lie in u1, therefore this will be less than or equal to this. You follow that? Therefore, what have we concluded? A in V is a local maximum for f composite h on V. Is that clear? Keep that in mind. Therefore, what do I know? I know d f composite h at A must be 0. See, notice that how we reduce. On S, I am unable to say anything because it may not be open, but we reduce the dimension. Okay, that is the power of implicit function theorem and our formulation also. Please understand that. Otherwise, it will be more difficult. Right? Do you understand this? What does this mean? This means df of h of a. H of a is a comma b acting on dha. Okay, this is 0. That means when it operates on Rn, okay, this is 0. Therefore, what I know is kernel of d of f of a b contains dha of Rn. You follow that? dfab acting on this space, and what do I know? We know this is n-dimensional, yeah, because dfha we saw it's of rank n. Yeah, it's of rank n. Therefore, the image will be an n-dimensional subspace of Rn plus k. Yeah, you understand this? Very good. Therefore, dimension of a kernel of dfab, that is p, must be greater than or equal to n. Yeah, do all of you understand? Keep that in mind. Okay, now let's look at G composite H. This we had already seen many times in the last lecture. This is identically 0 of x is 0 for every x in H. Why? That will be G of x hx, and where does it lie? It lies in, yes, this one. Therefore, this is 0 on, yes, G is 0, therefore it's identically 0. Therefore, what can I conclude? I can conclude dg of x, okay, and h of x acting on dh of x is 0. So I'm interested only at the point A, so let me rewrite this. So I have dg of x equal to A, h of A will be B, therefore it is dg of P acting on dha, this acting on Rn is 0. Do all of you understand this? Yeah, very good. Okay, so keep this also in mind. Okay, therefore kernel of dgp also is of dimension greater than or equal to n. Pause, review, proceed. Now what do I do? Now let's look at the matrix A, which is gradient of f1, sorry, gradient of f at p, and gradient of g1 at p, gradient of dgk at p. Okay, Now remember, f is from where to where? All these f, g, these are all functions from Rn plus k to r. Therefore, all these gradients, del f at p and del g at p, they are elements in Rn plus k. Right? So this matrix, therefore I start with any vector, okay, xi, which is x comma y in Rn plus k. What do I know? Okay, so what I know is this acting on, okay, dHa of Rn. Notice that dHa of Rn is an n-dimensional subspace of Rn plus k. Okay, this is 0. Yeah, do all of you understand this? Yeah. Now what kind of a matrix this is? As I said, this is n plus k, there are k plus 1, therefore this is k plus 1 cross n plus k type, the matrix of type. Okay, therefore what could be the maximum rank of this? Maybe k plus 1. Okay, where does it takes place? Therefore this map, okay, this A maps Rn plus k to Rn plus 1. Do all of you agree? Yes? Okay. K plus 1, sorry. Yeah, this is k plus 1, therefore it will map to Rk plus 1. K plus 1 cross n plus k, right? Let me just write so that do all of you understand this? And what do I know about this? So kernel of A, okay, contains what? dHa of Rn, which is n-dimensional, right? Therefore, by rank nullity, what do I know? N plus k must be equal to, okay, dimension of the image of A, that is the rank, plus dimension of the kernel of A. Okay, and this I know is at least n dimension. Therefore, dimension of kernel of A is greater than or equal to n from this. Do you follow that? Therefore, what do I know about dimension of image of A? Therefore, dimension of image of A is n plus k, okay, and this is greater than or equal to n. Therefore, minus of that will be less than or equal to n. Therefore, this is less than or equal to n, that is equal to k. Just make sure you follow that. Yeah, I am transferring this and use this inequality. Therefore, dimension of image of A is at most k. Therefore, that means rank of A is less than or equal to k. Do you agree that with this? Now go back to what we did. This A is a matrix of size k plus 1 times n plus k. Therefore, what is the maximum possible rank of A? That is k plus 1. What you are saying, its rank is at most k. So what does that mean? Now there are k plus 1 row vectors, okay, and you know matrix rank is same as the number of maximum number of linearly independent rows also, right? Therefore it will the maximum number, are you following? Rank of A equal to row rank of A, but row rank of A is at most k, but how many rows are there? K plus 1 rows. So what does it say? All the k plus 1 rows, these are linearly dependent. Yeah, therefore the rows, the k plus 1 rows are linearly dependent. Yeah, that means what? There exist scalars lambda, lambda 1, lambda k, not all 0. Okay, so that what happens? Lambda nabla f at p plus lambda 1 nabla f at g1 at p plus dot 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 nabla lambda k nabla gk at p, this is equal to 0. Okay, these are all at p. Yeah, right. Now can lambda be 0? If lambda is 0, what does it mean? That means this lambda 1 to lambda k, one of them is non-zero. That means lambda 1 to lambda k is not 0 vector. That means lambda g1 at p, lambda gk at p, they are linearly dependent, right? But what is this? Your dg at p is precisely this vectors, lambda g1 at p, lambda gk at p. Yeah, right? So what I know, this rank of this is k, and you are saying they are linearly dependent. That's a contradiction. Therefore lambda is not equal to 0. Pause, review, proceed. If lambda is not equal to 0, then I got it. Then what do I have? Delta f at p equal to minus of 1 by lambda summation lambda j del gj at p j equal to 1 to k. Okay, these are your things. Okay, so this proves a result. Go through the proof. Don't you think that proof is very elegant and very simple? Just very nice application. In principle, you don't want to understand the geometry of the implicit function theorem. You can start with the statement. You can use the implicit function theorem the way we formulated. Okay, then the proof is straightforward. I hope all of you like it. Okay, right. Now let's give, since I have time, let me give a nice application, my favorite application. Suppose A is an n cross n symmetric real matrix. Okay, what I want to prove is there exists a real eigenvalue. There exists a real eigenvalue. That is, there exists lambda in R and a non-zero vector in Rn, so that AV equal to lambda times V. This is actually the so-called spectral theorem, finite dimensional spectral theorem for real symmetric matrix. Okay, this is the most crucial step in the so-called spectral theorem. Many people may not even realize. Okay, the most crucial step is to prove for any given real symmetric matrix there is at least one real eigenvalue. After that, induction takes over. Okay, for details you can consult my book on linear algebra. Okay, anyway, this is all I want to prove. Right, now how do I prove it? Okay, I am going to make use of various results I have done already in our course on differential calculus of several variables. If you are not gone through it, okay, then you will have trouble. Okay, let me warn it. So what I want to do is I am going to look at a function from f from Rn to R. Okay, what is the function? F of any vector x is ax dot x. This is the usual dot product or Euclidean inner product. Right? And if you write in terms of coordinates, is going to be aij, xi, xj, I and j varying from 1 to n. This is a polynomial, quadratic polynomial. Therefore, this is a continuous and differentiable, etc., etc., etc. But if you remember, we had already computed the derivative in one of our earlier lectures. Okay, please go back and learn in case you have not done that, because this kind of examples are never done in calculus of several variables. So what you have found is, we have found out dfx acting on any h. This is any h Rn. Okay, yeah, the way we did that was, I will quickly do that, ax x plus h minus afx dot x, and use that. Then you will have ax dot x plus ax dot h plus ah dot x plus ah dot h minus ax dot x. So using symmetry, this is same as 2ax dot h plus ah dot h. Okay, so this suggests my derivative dfx acting on h. All these things we proved 2ax dot h. Therefore, what is the gradient of this function? 2ax. This is the vector. Beautiful. Yeah, good. Right. You understand that? Now this is a continuous function for immaterial of what point I had computed the derivative. Now remember, okay, I want to use, what do I want to do is the following. So let us look at the constraint g of x equal to x dot x minus 1. Then what is g inverse of 0? This is the usual sphere. Okay, n minus 1 dimensional sphere. For example, if R2, this will be circle. For R3, it will be standard sphere with the center at origin radius 1. And again, we had computed what is nabla g of x. Here notice that this is nothing other than ax, a equal to identity matrix. Therefore, this is going to be 2x. Okay. I'm just appealing to the earlier case. And this is a constant is 1, therefore derivative will be 0. I only have to compute the derivative of x dot x. That we had that is a special case of this earlier result where A is the symmetric matrix, identity matrix. Now what do I know? Now let us look at this set by Heine-Borel theorem. This is compact, closed and bounded. Why it's closed? G is a continuous function, differentiable, therefore G inverse of 0. 0 is a singleton is a closed set, therefore it's closed. Why it's bounded? Each of the vectors here has norm 1. Therefore it's a closed and bounded. Therefore by Heine-Borel theorem, we know it is compact. Since it's compact, what do I know? Now notice that now my S equal to Sn minus 1 is a compact set. Okay, it's not open or anything, it's a closed and bounded set, right? And on the function g, which is continuous or differentiable on all of Rn when restricted to this, is again continuous, but on the compact set there is a point A in the compact set Sn minus 1 such that A is a point of maximum. It's a global maximum. So in particular for every x in S, my g of x will be less than or equal to g of A. Do all of you understand this? Okay, pause, review, proceed. Right? Now what kind of A it is? That I know. At the point A, I know the gradient of the function and the gradient of the constraints. Okay, they must be scalar multiples of each other, right? Therefore okay, that means there exists a scalar lambda in R, so that what happens, the gradient of f at A should be equal to lambda times the gradient of g at A. What is this? This is 2 times A vector A, and this is lambda 2 times A, because the gradient is 2x. Yeah, that means there exists a vector, this vector v at okay, this vector, call it v, then I have AV equal to lambda v. And what is lambda? Do I have any idea what this lambda is? So we found it. Okay, we proved. What did we prove? We proved that there exists a real eigenvalue lambda, because there is an eigenvector v, and this eigenvector v belongs to the sphere, therefore norm v will be 1. And this has actually says something much more. I know what is lambda. Do I know what is lambda? Very easy. Look at AB dot v. That is lambda v dot v. That is lambda. But AB dot v is nothing other than f of v. But f of v is, I just called v nothing other than f of a. Therefore, this is the maximum of f on S. Okay. Therefore, lambda is nothing other than maximum. Similarly, you can do a minimum also. That also will have. Okay. So I hope all of you like this lecture. In case you are one of those guys who are too formal, you don't like the intuition, geometry, etc. Okay, you can ignore my first lecture, right? Stick to the second lecture. Within about 30-35 minutes, you have a very nice, neat, simple proof and a very beautiful application. Yeah, I hope all of you like it. Okay, stay tuned. We will meet again. Take care and stay safe.